I'm sure we've all seen the breathtaking imagery from the Hubble Space Telescope of beautiful and multicolored nebula. It almost seems as if a contemporary artist flicked different colors onto a canvas. But this isn't just a pretty picture. What you are seeing here are actual structures, tens to thousands of light years across. But how are these images so colorful? Does it really appear like that in real life? To answer this question, let's give you some context. Nebula may appear solid or maybe even like clouds, but that is far from reality. Nebula are extremely diffuse gas clouds. On average, you may get about 10 to 100 particles per cubic centimeter. This is far less than any artificial vacuum produced on Earth. To give you a sense of how little that really is, a comparable cubic centimeter at sea level on Earth contains 10 quintillion particles. That's 10 to the power of 19 particles. On the other hand, if you were to have a nebula the size of Earth, it may only have a total mass of a few kilograms. Orion, perhaps the brightest nebula in our sky, is just about bright enough to be seen with the naked eye on a clear night. However, nebula can be a lot brighter too. If the Tarantula Nebula, found in the large Magellanic Cloud, was as close to us as the Orion Nebula is, it would even be visible during the day. But if nebula are so sparse, how can we see them at all? It's important to remember the scales that are at play here. While nebula are sparse, they are also massive. H2 regions, which are a specific type of nebula, are known as stellar nurseries. These massive clouds can collapse and coalesce, and when they do, they form stars. A single nebula can contain enough mass to create hundreds to thousands of stars, and it is actually these newly formed stars that light up the gas in a nebula. Solar radiation shoots away from stars within a nebula, ionizing the nebula's particles, which releases this energy at a specific light wavelength. This means H2 regions are known as something called emission nebula, because ionized atoms within are emitting their own light. The process happening in an emission nebula is comparable to what happens in a neon light, where electricity ionizes neon within the bulb, causing it to light up. However, in a nebula, it's not neon that lights up. In fact, in the Hubble images, each color shows a different ionized atom. Unfortunately though, I can't tell you a blanket rule for colors in Hubble images. So while in this image of the Carina Nebula, reds correspond to sulfur atoms, greens to hydrogen, and blues to oxygen, in this image of the Swan Nebula, blues correspond to visible light blues, greens to oxygen, and reds to infrared and hydrogen. That's because of the way Hubble takes its photos. Hubble is primarily a visible light telescope, but its optical range does also extend into the ultraviolet and infrared. When scientists look at a nebula, they often want to see what it is made of, so will photograph the object using specific filters. So, say they want to see hydrogen in a nebula. They will image the nebula using a filter that lets light being emitted along 658 nanometer wavelengths through, or in other words, the emission band of hydrogen. After that, they are left with a black and white image. Then they may decide to image the nebula again, this time looking for sulfur along 672 nanometer wavelengths. And then again, looking for oxygen along 501 nanometer wavelengths. Scientists then assign colors to each of these different photos and combine them together to produce the colors you see here. As you browse Hubble images on their website, you can see for yourself what the colors have been assigned to by looking to see what wavelengths of light were used. For Hubble images of nebula, they are pretty much always a false color. However, Hubble does also take natural color images too. The Sombrero Galaxy, for instance, had 3 different images taken in blue, red, and green, or RGB. So the colors you see here are how you would see this galaxy, were it bright enough for you to see it. So, if Hubble's images of nebula are false color, what would they really look like to us? Generally speaking, a lot more red. The European Southern Observatory also looks at a lot of the same objects Hubble does, although often using different colour filters. Going back to the Carina Nebula, on ESO's website, we see that the colour bands are RGB or natural light, so we know that what we are seeing here is the Carina Nebula as we would see it. Here's ESO's version of Orion, except this time with ultraviolet and hydrogen overlaid on top of natural colours. So far we've only discussed the most famous nebula type, H2 regions or emission nebula. However, it is worth mentioning that there are a few other types of nebula too. You also have reflection nebula, where the energy from stars isn't enough to ionize the nebula. Instead, it reflects or scatters the starlight, meaning these nebula tend to have similar frequency spectrums to nearby stars, often appearing slightly bluish. You also have dark nebula, or nebula with no stars around them to illuminate them. These almost appear pitch black. All in all, nebula are not as colourful as you may have initially thought, but to me that doesn't make them any less interesting. Looking through these filters means we can understand a lot more about nebula than we otherwise could have, and they do make for beautiful images. Hubble has released a zip file on their website containing the top 100 pictures Hubble has ever taken. What I'll do over the course of this series is go through these pictures one by one and explain what it is you're looking at. And believe me, some of these pictures require an explanation. Episode 3. We're making good progress now, but I'm gonna have to do something a little bit unusual for this series. Number 21. The Carina Nebula. It hardly needs to be said, but this is a gorgeous image. It looks to me like an artist has flick painted a canvas in a spectacular way. But incredibly, the colours and shapes we see are actually representative of something real. Now hold on to your seats, because it's the only image we're going to look at today. There's simply too much to talk about, and I don't want to have to cut out any interesting details, which is good for me and for you. So to start off, where is it? The Carina Nebula is actually brighter and bigger at 200 light years across than the famous Orion Nebula we discussed in the previous episode, but it isn't as well known. This is because it's only visible from the southern hemisphere, meaning us up north won't be able to see it in the sky. It's found near the Carina constellation and is in the disk of the Milky Way galaxy. It's only 6,500 light years away from Earth, yet can be seen with surprising clarity with a long exposure camera or a small telescope. What we're seeing in this image is like the other nebula we've seen so far, the effects of extremely hot, young, massive stars blasting away at the dust and gas of the nebula. This, as we know, encourages star formation, and this nebula has plenty of star forming regions. Just off this main image here is the most luminous star in the Milky Way, WR25. Thankfully it's easy to find because this dust structure, known as the finger of God, is pointing at it. It's a staggering 6.3 million times more luminous than our Sun. It's part of a binary star system, but the two stars can't be distinguished in this image. We have to zoom in further to see them. The companion is thought to contribute about 15% to WR25's total luminosity. It is absolutely blasting away at this nebula. The finger and the surrounding globules are being evaporated into space, possibly even causing star formation there too. Even though it's reasonably close to us and is the brightest star in the galaxy, it can't actually be seen with the naked eye. There's too much dust and gas deflecting and absorbing its light. This image we're looking at included infrared data, which can see through dust and gas a lot easier than visible light. The colours of this image are significant too. Red represents sulfur, green is hydrogen, and blue is oxygen. This whole region of stars is the star cluster known as Tarantula 16. Also contained within this cluster is the massive and famous Eta Carina. Although not quite as bright as WR25, it's still over 4 million times more luminous than our Sun and over 100 times more massive. It again is part of a binary star system, the other star making total luminosity over 5 million times that of the Sun. Now imagine the Sun, and then imagine it 5 million times brighter. If you're doing it right, what you should be doing is imagining instantly and spontaneously combusting. Let's see why. So this is a hypothetical but similar binary star system, and this is a hypothetical planet which is a little further away than what Neptune is to our Sun. Its surface temperature is 500 degrees centigrade. On Neptune, it's minus 200. The Sun looks tiny in comparison, and Neptune really is this dim. So Eta Carina is pretty impressive then. It is a luminous blue variable star, meaning its brightness is changing over time. Only 150 years ago, it was the second brightest star in our sky, before fading to below naked eye visibility. The reason for this is because the star almost went supernova. This image of the star is the most detailed and highest resolution of an extended object ever captured by Hubble. Structures only 10 billion kilometers across can be seen with surprising clarity. What we're looking at here is the ejected mass of the star when it brightened 150 years ago. It actually got as bright as a supernova explosion, but somehow survived. During the explosion though, it did release mass in the form of two polar lobes and an equatorial disk, all moving outward at a speed of 2 million kilometers an hour. Since the explosion 150 years ago, it has increased in brightness and is now comfortably visible to the naked eye. Chances are it will still go supernova as it really is at the end of its life, and could do so at any moment. Now, there are three possibilities of the fate of this star. First is it could go supernova in a typical manner, where its core collapses and it would temporarily appear as bright as Venus in the sky. It could also go hypernova, potentially being the brightest supernova in recorded history, and a long duration gamma ray burst would knock out all of the satellites in our space. Although we humans with our feet firmly on Earth would be protected by the atmosphere. The last and most unlikely possibility is that it collapses into a black hole. Now, fun/horrifying fact, if it did that and one of Eta Carina's polar axis was aimed at Earth, collapsing into a black hole would likely give off a gamma ray burst, which would strike the Earth's atmosphere. This would be the equivalent to 1 kiloton of TNT per square kilometer over the entire hemisphere facing the star, effectively meaning the end of the world. Don't worry though, its axis isn't currently facing us and it's not really expected to give off a gamma ray burst, but it is food for thought nonetheless. Near Eta Carina is the Keyhole Nebula, a structure of dark, cool gas and dust, and also bright fluorescent gas. Eta Carina has a big effect on the nebula, ionizing gas and pushing against the surrounding dust. These bubbles and lines you see are due to the effects of this star. Also in the Carina Nebula is the famous Mystic Mountain, which you've probably seen before, and it is an image we'll discuss later in this series. To me though, it looks more like a man with a wizard's hat going on a leisurely stroll, but maybe that's just me. The last thing we'll look at today is Tarantula 14, the other big star cluster in this image. It's one of the youngest known clusters, and it contains about 2,000 stars. They are thought to be only 300 to 500,000 years old, which is very young for astronomical standards. They're extremely hot and will only be short-lived. They will likely dissipate in the next few 100 million years, so enjoy them while you can.
Have you ever wondered what it would be like for our solar system to reside in a nebula like this one? Glorious colours with huge structures stretching across the sky. It must be a pretty cool sight. Well, depending on how you define what a nebula is, it may surprise you to find out that we are actually inside of one, called the local interstellar cloud. How can this be? Well, let's understand first of all what a nebula actually is. The term nebula is a blanket term for a variety of different things. The word is a relic from early astronomy, where everything that looked a bit milky, foggy, or cloud-like was called a nebula, including what we now know are galaxies and star clusters. However, these days, we do have a bit more of a handle on what we classify as a nebula. The most famous type of nebula is the H2 nebula, an emission nebula like Orion, which consists of ionized particles, predominantly hydrogen. They are emission nebula because they emit their own light, as ionizing radiation from the young stars found in the middle of them excite the particles to higher energies, much like a neon lamp. On the other hand, there are also dark nebula, or molecular clouds, where there are no nearby stars, so ionization is not taking place. They often consist of dust and molecular hydrogen. Sometimes you can have a mix of the two nebulae, a dark nebula found in the middle of an H2 region. In such a situation, you can often see the outer particles becoming ionized, with the cold particles still found towards the center. It is especially in regions like these, where dark nebulae become eroded by ionizing radiation, that stars can start to form. In another situation, you can have light from stars shining on a dark nebula, but the energy isn't enough to ionize the particles within it. In this case, you have a reflection nebula, a nebula that simply reflects the light shining on it. The next two types of nebulae are also related. Planetary nebula, where a low to medium mass star has begun to shed its atmosphere and outer layers during its stellar evolution, usually before it becomes a white dwarf. The second type is a supernova remnant, usually the remains of a high-mass star after it went supernova, leaving behind a black hole or a neutron star in the center. These two types of nebula are so colorful and pretty because they also consist of ionized particles, charged from the respective events that caused them, so they are a type of emission nebula. Eventually, they will dim and disperse. Now, as you can see, all these nebulae can be categorized into two groups: emission nebula and dark nebula. These two categories have one big similarity: they are all diffuse nebulae. They extend for sometimes up to thousands of light years, and the particles within them are extremely spread out. Some of these nebulae only have a few particles per cubic centimeter, although some can have hundreds. But that still means that an Earth-sized nebula would only weigh a few kilograms. To give you some real perspective, sea level on Earth has 15 quintillion particles per cubic centimeter, and 450 kilometers up, which is slightly higher than the altitude the ISS orbits, there are still 50 million particles per cubic centimeter. So, when we see a nebula, we have the advantage of squeezing very diffuse objects into quite a narrow field of view, which means for objects like Orion, we probably have a better view of its structure than what any locals would have from the inside, because for them it's a lot more spread out. Chances are that if you were on an Earth-like body inside of a typical nebula, you wouldn't be able to tell you are in one with your naked eyes. That's not to say that all nebulae are equal though. The Tarantula Nebula, found in the Large Magellanic Cloud, is said to be such a bright H2 emission nebula that if it were to be where the Orion Nebula is, it would cast shadows at night for us and be visible during the day. A nebula this bright probably could be visible if you were inside it. As for our own local interstellar cloud, it too is an emission type nebula, likely a very dispersed supernova remnant nebula, mixed in with some cold neutral atoms. The ionized particles within it are exceptionally hot, around 6,730 degrees Celsius, with some particles even approaching millions of degrees Celsius. However, its heat-specific capacity is very low, because the density of particles is so sparse, at only 0.3 particles per cubic centimeter, meaning being out in the middle of it would barely heat you up at all. Unsurprisingly, this extreme sparsity of particles means our local interstellar cloud is not very bright, In fact, it is very hard to see at all, even with the most powerful of scientific instruments. That's because it really is on the boundary of what you might call a nebula, although we are starting to find out that, like the spectacular images of nebulae we already know, it too has a structure. This cloud is about 30 light years across, and interestingly, we seem to be moving through it, and will likely leave it altogether in about 20,000 years. That's because the Sun seems to be taking us in this direction, while the interstellar cloud is heading this way. So, if you've ever seen images of the solar system interacting with interstellar wind, it's not just the particles that are blowing around our solar system, but it's also a combination of us moving through it. The magnetic field of the Sun pushes ionized particles around the entire solar system, leaving behind a magnetotail as it travels, like a wake following a boat. While we don't have a real visual image of that for our own Sun, as again it's hard to see from the inside, we have seen it elsewhere in the galaxy. However, it's only ionized particles that interact with our Sun's magnetic field. Non-ionized neutral particles pass right through the magnetic field, going right through our solar system. This is how we've been able to tell which way the interstellar wind comes from. We've had spacecraft in orbit detecting the direction of these neutral particles as they pass through. Even though the interstellar cloud is not dense compared to other nebulae, it is actually one of the densest regions for hundreds of light years in any direction. This is because it is contained in a region known as the local bubble, where the average density is even lower than the local interstellar cloud at 0.05 particles per cubic centimeter. Interestingly, this bubble connects two other bubbles, and it's in the regions where these bubbles meet where it's believed that clouds like the interstellar cloud form. Let me explain. When we talk of nebula of any kind of density, we are actually talking about the interstellar medium. The interstellar medium, simply put, is all the gas and dust found in the galaxy, in whatever form that may be. It isn't evenly distributed, and the thickest sections of it are the different types of nebula we have already talked about. However, if you look anywhere in the sky, and look through the right wavelengths, you will see a faint glow in space. These are ionized particles emitting electromagnetic radiation in a variety of frequencies. So, the local interstellar cloud is part of the interstellar medium. But as I mentioned, it isn't evenly distributed. Within our local bubble, the density of the interstellar medium is far below the average of the whole Milky Way. This is because these bubbles are thought to be the result of supernovae explosions millions of years ago. The supernovae not only ionized the particles, it also pushed most of them outward, leaving behind the bubbles, or what is known as supershells. When supernovae shockwaves meet, the particles suddenly have nowhere to go, so instead they clump up. It is believed that our own local interstellar cloud comes from where our own local bubble and another bubble met. There are plenty of bubbles out there, and the resulting local map of our galaxy's interstellar medium looks quite messy. You may wonder though, why is any of this important? What's the point of scientists trying to figure this out? Well, it is important to understand our local space environment because it helps us better define the universe around us. When we are observing something far away, we can remove contamination from any readings caused by the local interstellar cloud surrounding us, because we now know what we can expect from it. Also, better understanding the interstellar wind coming into our solar system means we can better protect astronauts against it. So, there we have it. While we may not be in a nebula as spectacular as something like Orion, we are right in the middle of our own local interstellar cloud, which has a structure and that emits its own light. Hubble has been in orbit around Earth for more than 30 years now, and it gave scientists a bit of a scare at the beginning of March when it encountered some problems with its onboard computer. Thankfully, the mission team has since successfully recovered Hubble, and everything is functioning as normal.
Hubble's mission is due to continue for many years yet. Scientists expect Hubble to continue on until the late 2030s. So what are some of the incredible discoveries it has made so far? Well, today I wanted to focus on one of the most beautiful aspects of space. A wide-angled, uninterrupted view of the sky reveals something quite remarkable. There are literally hundreds of nebulae spread out across our view, the birthing place from which all stars come from. But the term nebula covers a lot of different types of interstellar clouds, each with unique and beautiful characteristics. I'm Alex McColgan and you're watching Astrum, and in this episode of the Hubble Images series, we are going to explore a variety of spectacular nebulae that Hubble has examined, and I'll explain to you what it is you're looking at. The first thing to quickly explain before jumping into the Hubble images is that all nebulae are part of something called the interstellar medium. The interstellar medium is the gas and dust that is unevenly dispersed around our galaxy. This is what the interstellar medium looks like from our viewpoint on Earth. Some parts of it only have one particle per cubic centimeter, as close to a true vacuum as you can get. The densest regions, which are like the nebulae I'm about to show you, can have millions of particles per cubic centimeter, which is still incredibly dispersed if you consider our atmosphere has 10 quintillion particles per cubic centimeter at sea level. However, over the many light years these nebulae stretch across, this mass really adds up. Let's look at our first example and I'll show you what I mean. Number 61, the Circinus molecular cloud. The most basic type of nebula is an inert, cold and dark nebula, also known as a molecular cloud. They are named like this because they mainly consist of the molecule H2. In this state they don't do much, and we can only really see them because they block the light behind them. However, molecular clouds are some of the most densely packed nebulae out there, with millions of particles per cubic centimeter. They sit in space for millions of years, prevented from collapsing in on themselves by their own internal pressure. That is, until an external force comes along and bumps the cloud. This force could be from a supernova shockwave or from density waves in the galaxy. In any case, this nudge overcomes the internal pressure of the cloud, causing it to start collapsing in on itself from its own gravity. And the result is what you see tucked into the center of the Circinus molecular cloud, a star being born. This entire cloud has 250,000 times the mass of our Sun, meaning if the whole thing collapses, there's going to be a lot of stars in this spot in several million years. If we zoom in on the star that has already formed, we can see some interesting phenomena. The bright nebula surrounding the star is still part of the Circinus molecular cloud, it has just been lit up from the light of the young star. This region is known as a reflection nebula, a nebula that simply reflects the light shining on it. You can also just about see a protostellar jet shooting away from the star, the leftovers from the gas and dust it absorbed from the molecular cloud. It's a different color because it's really hot, having come from the star itself. Let's move on to number 62, NGC 2014 and NGC 2020. This breathtaking image is a great example of one of the most famous types of nebula, known as an H2 region. H2 regions are basically what happens to a molecular cloud once star formation has really gotten going. The biggest difference between a molecular cloud and an H2 region is that an H2 region produces its own light. The particles within it have been ionized by the solar wind and UV light from the young, hot stars shining within them. H2 regions also tend to be a little less dense than molecular clouds, having only hundreds to thousands of particles per cubic centimeter. In this particular image, you have what appears to be two separate nebulae side by side, but actually they are part of the same cloud. It's just that only two parts of the cloud have been carved out and ionized so far. The different colors come from the differences in ionized materials. In the red section, the ionized gas is hydrogen. In the blue section, the ionized gas is oxygen. This difference is due to the way these two regions came to be. In the red section, you'll see hundreds to thousands of stars, each more than 10 times the mass of our Sun. It's UV radiation from these stars that is ionizing the hydrogen around them. Stellar winds from the stars can be seen carving out the nebula. Here, the nebula is dense, and so is more resistant to the stellar wind. Here, however, the nebula is less dense, and the stellar wind has carved bubble shapes into it, reminiscent of coral. The blue region, unlike the red region, has been shaped by a single, massive star known as a Wolf-Rayet star. This type of star is the hottest and most luminous star out there, this one being 200,000 times more luminous than our Sun. Because it is so hot and luminous, its expected lifespan is very short, only a few million years, and over the course of that time, it is shedding a lot of its mass in the form of powerful stellar wind. It's this wind which has interacted with the oxygen specifically, increasing its temperature to over 11,000 degrees Celsius, which is way hotter than the ionized hydrogen also in the nebula. You can see a small section of the red nebula also has some heated oxygen towards the center, which beautifully looks like water lapping up against the beach. And to a lesser extent, there's some blue over here too. Overall, a stunning image from Hubble. Number 63, and a different type of nebula again with NGC 7027, or the Jewel Bug Nebula. The previous two types of nebula we looked at are closely related, unlike this beautiful type of nebula, which originates from something completely different. While molecular clouds and H2 regions span hundreds to thousands of light years, a planetary nebula like this one is only a couple of light years across at most. And while molecular clouds and H2 regions contain enough mass to produce thousands of stars, planetary nebulae barely contain enough for one. This is because this nebula is the result of an intermediate mass star on its last legs. The star at the center of this nebula is coughing and spluttering its outer shell into space before it contracts into a white dwarf star. Incredibly, because Hubble's mission has been going on for so long, it means we can sometimes see a tiny part of a planetary nebula's evolution. Here's number 64, the Stingray Nebula. This planetary nebula has changed drastically between 1996 and 2016. Just look at how it's dimmed over only 20 years. This is very unusual. Because of the vast timescales involved for us humans, usually we can only see limited movement over such a time frame. For example, number 65, the Cat's Eye Nebula. This planetary nebula has barely shifted at all over a similar timescale. It's not too hard to see why this nebula has the name it does, and it's really quite beautiful, both up close and more zoomed out, where you can see gas and dust that has been previously ejected. Planetary nebulae are somewhat similar to H2 regions in that they are both emission nebulae. They produce their own light through ionization of the gas particles from stellar winds. Let's have a look at another one. Number 66, NGC 7293, or the Helix Nebula. What a piece of art this is. The fascinating thing about planetary nebulae is that while some share similar characteristics, no planetary nebula is ever identical, and each produces its own unique fireworks display. And we are lucky to have witnessed these ones, because as planetary nebulae expand, disperse, and cool, they will be lost from view only tens of thousands of years after the event, leaving the tiny white dwarf star behind. Which means the ones we can see now happened very recently, astronomically speaking. And because they are so small compared to the other nebula types we've seen so far, they can only be spotted in our local galactic neighborhood. The Helix Nebula is especially close to us, being half the size of a full moon in our sky, which allows us to peer inside and see its remarkable details. What I think so incredible about this image is seeing how the stellar wind from just this one star is blasting away at the dust halo which had been ejected away from the star before the planetary nebula formed, just like the halo we saw in the Cat's Eye Nebula. With the Helix Nebula, the expansion of the planetary nebula has now caught up with the halo and is carving it away. This is a mind-blowing image of space, and it's probably one of my personal favourites. There are so many more beautiful examples of planetary nebulae that I could show you, but let's finish this episode on number 67, the Hourglass Nebula. This nebula is pretty far away at 8,000 light years, so we can't see it in the same detail as the Helix Nebula. However, its shape, colour and little beady eye in the centre are truly phenomenal. Sometimes, if the planetary nebula originated from a tightly orbiting binary star system, what you'll get is a two-lobed nebula. This could be the case for this one, and you can see the star or stars towards the centre here. No, this isn't the reflection from the camera flash that pareidolia would have you believe.
Episode 5. For the episode playlist, click on the annotation here or have a look in the description. Number 28, Doradus 30, or the Tarantula Nebula. This image is a small section of what is known as the Tarantula Nebula. The Tarantula Nebula is a huge, impressive nebula found in the Large Magellanic Cloud, a satellite galaxy to our own. Some may argue it isn't as pretty as some of the other nebula we've looked at so far, but I must say it does look good in its own right. But if it isn't its looks that make this nebula stand out, what is it and what sets it apart from anything we've looked at so far? Well, we'll come back to that. Let's first of all give you some context. So where is it? Well, this is the Large Magellanic Cloud, the largest of the Milky Way satellite galaxies, and as you see it has a lot of nebula. The one we're focusing on, the Tarantula Nebula, is the brightest and biggest nebula in this galaxy, and it really is bright. I selected this image because it still shows some of its details. Most other images I found show it as this bright, overexposed spot. It's so bright that if this nebula was as close to us as the Orion Nebula in our own Milky Way, it would cast shadows at night. Let's zoom in to find out why. The Tarantula Nebula is currently undergoing extreme star formation. In fact, it's the most active star forming region in the whole local cluster of galaxies. To its center is a region of stars known as NGC 2070. The central concentration of stars known as R136. It's this star cluster that produces most of the energy to make this nebula visible. It's a really big cluster with an estimated 450,000 solar masses contained within it. Now, if you've ever wondered what the most massive and brightest known star was, look no further. One of the stars in this cluster, known as R136A1, is the most massive and brightest star on record, with some pretty incredible statistics. It's a Wolf-Rayet star, 315 times the mass of the Sun, and 8.7 million times more luminous. It is also one of the hottest stars at 53,000 degrees. While it is the most massive star, it isn't the biggest, although its size still dwarfs the Sun. As always with these massive stars, it will only be short-lived, and it will almost certainly become a black hole at the end of its life. In the meantime, it's shedding its mass through solar wind at a very fast rate. Since its birth, it's thought it's already lost 50 solar masses to space. Overall, the R136 star cluster is thought to be only about 2 million years old. It's currently merging with another close-by cluster, the two clusters together making up NGC 2070. You may not think that there are enough stars in this image to make up 450,000 solar masses, but these blue stars you see in this image are only the very brightest O-type stars in the cluster. Interestingly, there is a star that belongs to this cluster, which isn't found anywhere in the area. If we zoom out a bit, you'll find this star over here. It's called 30 Doradus 016, and the young star, only 1 to 2 million years old, may have travelled about 375 light years from its suspected home
in the star cluster R136, and it's still travelling about 400,000 kilometers per hour. But how did it get all the way out here? The theory is that it was part of a binary star system when another, even more massive star entered the system and kicked out the now homeless star. These other stars would have had to have been extremely massive, as 30 Doradus 016 is no minnow at a suspected 90 solar masses. It is now an explorer destined to travel the far reaches of the Large Magellanic Cloud. There is another old star cluster found in the Tarantula Nebula called Hodge 301. It is roughly 20 million years old, with some stars 10 times as old as those found in R136. Within this star cluster, there are thought to have been at least 40 stars that have gone supernova, whereas in R136 there have been none. This is because of the age of Hodge 301. Some of the shortest lived stars have already gone through their entire life cycle. More stars in this cluster are on the verge of exploding in a supernova too, so watch this space. The original image we looked at is further away still from the centre of the Tarantula Nebula, although it's still part of it in an area called NGC 2060, found over here. It's a star cluster too, although the stars here are much more loosely dispersed than in R136 and Hodge 301. In fact, these stars are no longer gravitationally bound to each other, and in a few million years, the stellar group will disperse completely. It's currently about 10 million years old, and there are some very interesting things found in this area. The first I'll mention is that the whole of NGC 2060 is a supernova remnant, about 165 light years across. It's estimated that the supernova occurred about 4,000 to 5,000 years ago, and consistent with this theory, a pulsar neutron star is found in this area here around the same age as the supernova. It's not really visible in visible light, as it emits X-rays, which means you need the X-ray telescope Chandra to see it, and it's right in the middle of this bubble. The bubble itself is the supernova remnant. The pulsar rotates exceptionally fast, once every 16 milliseconds. Interestingly, it's not the fastest rotating star in this region. That accolade belongs to this runaway blue supergiant VFTS 102. It's actually the fastest rotating star that we know of, rotating a speedy 2 million kilometers per hour. This is 100 times faster than the rotational speed of our Sun. It spins so fast that the star is flattened, with an equatorial disk extending out due to centrifugal forces. It is suspected that this runaway star actually was part of the same system as the pulsar and would have had a hand in its supernova explosion. Before the supernova, they would have been two blue stars orbiting one another. One would have evolved into a red supergiant, and as it expanded, it would have started feeding its mass into the other star, speeding the rotation of the other. Once the red supergiant exploded in a supernova, it ejected the other star at a tremendous speed into space. VFTS 102 fits this model as it's spinning rapidly whilst also hurtling through space in relation to its stellar neighbourhood. Zooming out further again, we are getting to the edge of the Tarantula Nebula. At its longest points, the Tarantula Nebula is an incredible 1,000 light years across. I already mentioned this nebula is the most active star-forming nebula, known as an H2 region in our local cluster of galaxies, but it is also the biggest. If it was as close to us as the Orion Nebula, it would be twice as big in the sky as the Big Dipper, and because it's so bright, it would even be visible during the day. At the far edge of this nebula is perhaps its most remarkable visual spectacle. It's called SN 1987A, and it's a supernova remnant. It is a lot younger than any of the other supernova we've looked at so far. In fact, it's less than 30 years old. The light from this supernova hit Earth in 1987 and was visible to the naked eye. It was the first supernova observed since the 1600s, and the only supernova observed that we've had a close look at using modern day telescopes. When it exploded, it was a blue supergiant, which means it was only about 1/10 of the brightness of a red supergiant supernova. Haven't had the chance to look at it now. I bet you're wondering what these rings could be. Well, they are the mass thrown off by the star through stellar winds, coughing and spluttering its innards out thousands of years before the supernova. The initial flash from the explosion lit the rings up at first, but when the supernova's shockwave hit them a few years later, they lit up again due to interactions with the rings and the debris from the shockwave. SN 1987A is now a true supernova remnant, in the vein of Cassiopeia A, illuminated not by the explosion of the star, but by continual processes between the debris of the supernova and the material beyond it. This artist's illustration of SN 1987A is based on real data and reveals the cold inner regions of the exploded star's remnants, this patch here in red, where tremendous amounts of dust were detected and imaged by the ALMA telescope. It's in this dust that the leftover pulsar could be hiding, because nothing has been detected where the pulsar should be. Another option could be that it didn't turn into a pulsar at all, but is actually now a black hole.
The James Webb Space Telescope has been in space for over a year now. The images it takes of the universe continue to captivate with their high-resolution detail and breathtaking beauty. However, although it may sound counterintuitive, it is often what the Webb does not see that allows us to really shine a light on the universe's inner workings. This seeing without seeing might sound strange, but it's a foundation on which much modern observation of the universe is based. Through clever techniques, it allows us to understand the chemical composition of molecular clouds and nebulae, the makeup of atmospheres around exoplanets, and the existence of rings around asteroids in our own solar system. The James Webb Space Telescope is uniquely placed to take advantage of these clever techniques due to its unprecedented sensitivity and precision. I'm Alex McColgan, and you're watching Astrum. In this second video on the spectacular sights captured by the James Webb, I will show you the awesome power of not seeing, as well as seeing, in helping us expand our understanding of space around us. Let's begin with this image of NGC 346, a cluster of stars and associated nebula found in the small Magellanic Cloud, 210,000 light-years away from us. NGC 346 is interesting to scientists because the conditions and amount of metals found in this area are similar to the conditions back 2 billion years after the Big Bang, in a highly energetic period of the universe's history known as the Cosmic Noon. Countless stars and galaxies were rapidly forming during this point in time. By studying this nearby modern contemporary, scientists can get a better idea of what Cosmic Noon might have been like. But how do scientists know the metallic composition of these beautiful swirls of stellar matter? One method is through looking at emission lines. When gases get hot, say because they have been warmed up by a star, the atoms that make them up seek to dissipate that heat by emitting radiation. However, for reasons that have something to do with quantum mechanics, which we won't dive into here, every atom can only emit radiation at a specific, unique wavelength. This gives elements distinct chemical fingerprints. If you know the wavelengths of light given off by oxygen, you can always tell when superheated oxygen is the source of any light you come across. So, by seeing this light, the James Webb Space Telescope has an idea of the chemical composition of this nebula. The Webb is particularly suited to investigating nebula like these, as infrared is much more able to pierce dust clouds and see what lies at their heart. Webb's superior sensitivity allows it to detect details that had never been seen here before, including the small disks of dust that were forming around developing protostars, potentially even marking the beginnings of planets. However, these are standard methods of observation. I started this video by talking about seeing through not seeing. And when it comes to astronomy, merely looking at the light emitted by objects is often not enough. For instance, Recently, the Webb imaged this. This is an ice cloud. More specifically, it is the Chameleon-1 dark molecular cloud, another birthplace of stars. As you can imagine, an ice cloud is not hot enough to radiate light with emission lines. So here, scientists need to use a different technique to learn its chemical composition. But thanks to Webb's piercing vision, a different method can be employed. As I said earlier, when atoms become excited, they release radiation. But this process works in reverse too. When cold atoms are hit by radiation, they can become excited. They absorb the energy, becoming a little warmer. This has a clever implication. It means that if you shine a continuous spectrum of light through a gas cloud and see which frequencies of light get blocked by that cloud, it'll tell you just as certainly what elements make up that cloud as if you'd heated them up and they were radiating. This is what I mean by seeing through not seeing. Of course, it does hinge on light shining through the cloud you want to look at. This occurs through all the stars sending out light from behind the Chameleon-1 dark cloud. The light given off by stars is much more varied in its wavelength than the light given off by specific gases, as solid objects give off photons under different rules to gas. This provides a smooth, continuous light source to check absorption lines. There is a problem though. For objects as large as a molecular cloud, they can be too dense for starlight to be able to penetrate it. This is where the power of Webb comes into play. Thanks to the Webb's unprecedented sensitivity, for the first time, scientists have been able to detect the light from distant stars through the thick cloud of Chameleon-1, allowing them to see its chemical composition. What they found was a surprise. Not only does the Chameleon-1 dark cloud contain water ice, but also some of the fundamental building blocks of life: ammonia, methane, and methanol. This means that stars and planets that one day form in this icy cloud will start off with some quite complex chemicals to get the ball rolling. And if this turns out to be common, it makes it much more likely that worlds capable of bearing life are actually widespread throughout the universe, decreasing the likelihood that we are alone in it. Spectroscopy, the science of studying the chemical makeup of objects from their absorption lines, is a very versatile tool, and it extends to much more than molecular clouds or nebulae. Through it, we can also learn much about the atmospheres of exoplanets. Webb was able to discover the chemical makeup of one such exoplanet, WSP-39b, a Jupiter-sized exoplanet 700 light-years away from us, by waiting until it passed in front of its own star. Light from the star filtered through the planet's atmosphere, where the gases within absorbed the light at certain frequencies, leaving their distinct fingerprints on what remained. Webb detected sulfur dioxide in WSP-39b's atmosphere, the first time this compound had ever been seen in an atmosphere outside of our solar system. Webb also provided a complete breakdown of all other chemicals and elements present, including some water vapor. Spectroscopy, as impressive as it is, isn't the only way Webb makes discoveries by not seeing. There is a second process known as occultation that astronomers have been making use of over the last century. Rather than searching for the spectroscopic breakdown of the light from stars, watching for occultation involves noting a star's brightness over time. By looking out for the sudden dimming of stars, scientists can discern the presence and characteristics of dark objects that pass in front of them. And the James Webb Space Telescope is very good at spotting such dimming moments. In our solar system, between Saturn and Uranus, there lies a rather unusual asteroid called Chariklo. It is 250 kilometers in diameter and is the largest of the asteroids known as the Centaurs, asteroids that tend to orbit between Jupiter and Neptune. However, that is not its claim to fame. Chariklo is impressive because in 2013 it was discovered to be one of 5 objects in our solar system to have rings. For a while, scientists did not think that objects as small as Chariklo could support rings. Even now,
They are unsure whether these rings are only here because they are relatively new, forming in the last few million years or so, or whether some gravitational phenomenon caused something like Sheppard moons, keeping them in place. James Webb Space Telescope tested its ability to observe occultation by trying to spot these rings as Cheriklo passed in front of a distant star. This was not as easy to do as it sounds. It takes extremely precise predictions to know where Cheriklo would orbit, to know which star to watch. Given the size of objects in space, even the smallest miscalculation would result in no occultation being observed. That said, Webb was able to spot Cheriklo and its two rings as they passed in front of the star, noting the occultation of the asteroid itself as well as each of the rings, as seen in this video. The rings were too small to be imaged by Webb directly, but from the sudden dimming in the star's brightness, Webb was able to clearly make out the rings, which are thought to orbit about 400 kilometers from Cheriklo itself. The larger of the rings is only 6.9 kilometers wide, and the smaller one is a tiny 120 meters wide. It is not yet clear what these rings are made of, but Webb was able to detect crystalline water ice on the main body of Cheriklo. With further observations, more information about these rings will come to light. And speaking of rings, there is one more image I want to show you. This is just one that I found spectacular. The strange rings of Wolf-Rayet 140. These reddish purple rings are like nothing I've seen in space before. The astronomers who first saw it thought that something might be wrong with their equipment. The rings seem more like the ripples of a pool or the rings of a tree than an actual interstellar object. And yet, these rings actually represent over 100 years of a truly incredible phenomenon. At the heart of these rings lies a binary star system. Every 8 years, the two stars at the center of this system orbit close to each other, and their stellar winds interact in such a way as to blow a fresh ring of dust outward into space. There are at least 17 rings, meaning this process has been ticking along every 8 years for the last 130 years or so. This phenomenon is large. The furthest ring is 70,000 times the distance from the Earth to the Sun. The detail Webb was able to capture is incredible. Previous glimpses at this system indicated that there might have been one ring, but it's incredibly blurry compared to the resolution captured by Webb. These rings were useful for astronomers, as they provided opportunity to spatially document the chemical compositions of the rings of Wolf-Rayet 140 over time. Through these probes, scientists found what they believed to be polycyclic aromatic hydrocarbons. PAHs had been known for a long time. They help with the formation of stars and planets, but their origin has long been a mystery. Now, thanks to this discovery by the James Webb, Wolf-Rayet binary stars have stepped forward as one possible source for this crucial compound. And it was only possible because of the spectroscopy and James Webb's ability to see and not see light in incredible detail. There will no doubt be many more discoveries Webb will make in the years to come. Such a powerful telescope can capture images at far greater clarity than the space telescopes before it. But I thought it was important to emphasize that not all the Webb's discoveries are stunning images in the night sky. Many of its biggest breakthroughs lie in the tiny hidden details of things not seen. Light not appearing when it might be expected to, indicating the presence of hidden chemicals or celestial objects. Because it turns out, it's not always about what you see. Sometimes what you don't see is most informative. This is one of the most hotly requested topics for this channel. Even if you didn't actively request it yourself, you couldn't have missed the buzz around the James Webb Space Telescope. It is more powerful than any other space telescope, including Hubble. So big, it had to be folded up like origami to fit onto the rocket that carried it into space. So precise and sensitive, it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its sensors. So expensive, it cost $10 billion to make,
and so complicated it took decades to complete. 300 potential failure points stood between it and proper functionality. But now it is here. And it has an incredible mission: to study planetary systems for evidence of life, to understand the formation of planets, stars, and galaxies, and to peer out across the universe to objects so far away the light they gave off has been traveling for almost as long as the universe is believed to have existed. In other words, the James Webb Space Telescope was built to spot the first stars and galaxies at the very edge of our knowable universe, objects from the beginning of time. And the first images have started coming in. I'm Alex McColgan and you're watching Astrum. Join with me on a journey as we look over the early photographs coming out of the James Webb Space Telescope and see for ourselves the power and precision of this engineering miracle. It's already promising to be spectacular. For those who are new to this channel, we've already spent some time watching the James Webb Space Telescope as it's gone from a work in progress to a fully realized piece of hardware. It was first conceived in the 1990s and was originally intended to cost only $1 billion and to launch in 2007. However, numerous setbacks and delays plagued the project, pushing it back again and again. It was only in December 2021 that it finally launched, and it has been spending the intervening months slowly unpacking itself, powering up its systems, and testing its hardware. It is a 6,500 kilogram monster, with a sun shield whose 14 by 21 meter dimensions are around the size of a tennis court. Its mirror for capturing light is 6 times larger by area than Hubble's lens, which allows it to pick up more photons from further away to create crisp images. It boasts numerous cameras and scientific instruments which allow it to see across the infrared spectrum. This is a feature that is vital to its unique mission. Due to the expansion of the universe, all of the light from the furthest reaches of space have been stretched to the point that no matter what they were to start with, they are all at least infrared light now. So the only way to see these light sources is with an infrared telescope. On top of that, infrared is much better at punching through dust clouds and other obscuring debris, giving the James Webb Telescope the incredible ability to see objects that are beyond the sight of Hubble. I compare this telescope with Hubble a lot, as the James Webb Space Telescope was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble can mostly see in visible light spectrums, while the James Webb Space Telescope can almost exclusively see infrared and can't see some visible light spectrums at all. It's more accurate to say that the two telescopes complement each other rather than compete. They work together to form a powerful duo, expanding our understanding of the universe. But that's not what you're here for. You're here to see what James Webb can do. Beginning in our own galaxy, let's gradually expand our vision outwards towards the edge of the knowable universe. You are in for some spectacular sights. The first stop on our journey is a place known as the Cosmic Cliffs. The Cosmic Cliffs, otherwise known as NGC 3324, are part of the Carina Nebula, about 7,600 light-years away from us. These peaks you are looking at are massive structures, around 7 light-years high, and what you see here is only a portion of the nebula as a whole. The actual nebula is much larger and contains a hollowed-out center, where the stellar winds given off by stars have blasted all nearby dust away from them. What we are looking at here is the edge of this hollowed-out bubble. Scientists are very interested in this region of space for one simple reason. It helps answer questions about the formation of stars. Thanks to the stellar winds in this zone, dust and matter conglomerate together, forming a birthing place for stars. However, for all our stargazing, there are still many mysteries surrounding this process. How exactly do they form? What do the different stages look like? It's difficult to tell. Part of the difficulty with finding the answers is the dust itself, both vital to the process and also a massive impediment to seeing it happen. It wraps around the forming stars like a protective cocoon, stopping scientists from seeing very clearly what is going on at the moments we'd like to see the most. James Webb fixes that. Not only does this image provide more detail than Hubble's image, but thanks to James Webb's onboard MIRI, or mid-infrared instrument, we can peel back the layers of dust and see what lies within. See how much clearer the image is. This will provide scientists with data on the formation of stars for a long time yet. So much for the birth of stars. At our next stop, the James Webb Space Telescope uncovers more about the end of their lifespan. And for this, let's look a little closer to home to NGC 3132, otherwise known as the Southern Ring Nebula. The image on the left was taken by James Webb's near-infrared camera, while the one on the right was taken by MIRI. This is a planetary nebula, although technically that term is a bit of a misnomer. While regular nebulas are the birthplace of stars, a planetary nebula is not a place planets form. Instead, it was just an unhelpful naming convention used by early astronomers who noted the round shapes of these nebulas and they thought they looked a bit like planets. The name stuck, even though our interpretation of the name has moved on. Planetary nebulas like this one are formed when dust and gas are blasted out from dying stars towards the end of their lifetimes. Knowing the chemical composition of this dust is useful, as understanding what material exists in the universe helps us to understand what later waves of stars might be made of. So once again, James Webb's ability to peel back the layers of dust to see what lies within is invaluable. Compare this with Hubble's image to get a sense of the increased detail that James Webb is able to bring to bear. From this, scientists have learned that the second star within the system still has not actually exploded, so the formation of its own planetary nebula is still likely to come. We can also get a better sense of how the gravitational interactions of the two stars stir the nebula, mixing the dust together in fascinating patterns. Now, let's look a little further out, beyond our galaxy. If we want to see star creation, it makes sense to find a location like this. 161,000 light years away from us lies the Tarantula Nebula, so named because it evokes the idea of a giant tarantula lurking within its silken web. Aside from the obvious otherworldly beauty, this area is of particular note to scientists because of its similarity to a period in the universe's history known as the Cosmic Noon. At that point, which to our best understanding took place about 1 billion years after the universe began, star creation was at its most prolific. It is thought that conditions there would have looked something like this. James Webb has been able to spot stars here that are only just coming into being, a fascinating period of time to study. Let's look further out again. As our gaze extends, we lose track of individual stars and start seeing things on a galactic scale. Even here, there are beautiful dances being played out. Stephan's quintet is a formation of 5 galaxies, although one is not really next to the others, but just looks that way from our perspective. Famous for being featured in the film It's a Wonderful Life, it is thought that 4 of these galaxies will one day collide. Indeed, 2 are already doing so. James Webb allows us to see clearly the brilliantly hot dust being kicked off as these 2 central galaxies circle each other. The gravitational forces here are mind-bogglingly intense, the energy profound. It is a dance that is truly only appreciable at scales like this one. This image was not taken at a single time, but actually is a composition of almost 1,000 separate images that James Webb took and then scientists put together, giving it incredible resolution for picking out details. Let's look further out again, until even James Webb is straining to see, in an image known as Webb's first deep field. This image is taken from an area so small, a single grain of sand held out at arm's length would block it from your view in the night sky. At this scale, individual stars are almost completely absent. Most of what you can see here are not stars, which would be too small to detect on their own, but galaxies. Here you can see the fish lens effects being created by gravitational warping, as relatively nearer objects bend light around them, distorting what lies beyond. We start to see the edges of the universe.
In this image is one of the oldest galaxies we have ever sighted. It is so far away, the light from it, when it was born at the beginning of the universe, has only just reached us. Where is it? We are going to need to zoom in. Do you see it? It's admittedly quite small. By evaluating markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus how long the light from it has been traveling by comparing it to normal visible light from similar sources. This tiny dot was found to be 13.1 billion light years away. As far as we know, given that the universe is thought to be 13.7 billion years old, this is one of the earliest galaxies that we will ever be able to see. Now, you might be disappointed by how small it is. However, there is some room for hope. Compare this image with one taken by Hubble of the same region. Obviously, James Webb's image is crisper and clearer, giving more detail and showing more objects. But there is one vital distinction between these two images. Hubble took its image by staring at this patch of sky for 10 days, slowly gathering every photon it could from this region of space and compiling them into a single image. James Webb, on the other hand, took only half a day taking its own image. What this implies is that if James Webb was able to take such a detailed image in 1/20th of the time, imagine how detailed an image it could take if it was given a comparable amount of time. In other words, this tiny little dot is likely not the best that James Webb can do. I hope these images have given you a sense of the scientific breakthroughs possible with the James Webb Space Telescope, but also just how beautiful the sights of the universe are. Images like these blew me away. Sadly, we are going to have to be a little patient to see what discoveries James Webb might have in store for us. James Webb has only just finished running through its calibrations, letting its instruments cool off and making sure everything is working perfectly. There are queues of scientists fighting over who gets to use it to do what over the next 5 to 10 years of its expected lifespan. Each second is hotly contested. It will be investigating exoplanets for signs of hospitable atmospheres for life, unveiling nebula to find the origin of stars, and will help us to understand the difference between an old galaxy like ours and the young galaxies that formed just after the Big Bang. With a tool as powerful as the James Webb Space Telescope, who knows what else we are about to discover. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.